Hi everyone, welcome to week 10. We're going to look at standard deviation this week. So last week we were interested in, where's the center of the data, measures of central tendency. This week we're interested in how spread is the data, okay? Was it all tied around the mean, or was it really widely distributed? Was it skewed? Just what was the distribution like? So as you see, there are two measures we're going to talk about. One is range, one is standard deviation. Now range is the most simplistic measure we can give of the spread of the data. It's just the difference between the largest and the smallest score. So in this, look at this data set here, 1, 2, 3, 3, 3, 4, 100. So its range is 100 minus 1, which is 99. It's useful in the way that it tells us, okay, the results are very widespread, but that's just two numbers were picked on there, 1 and 100. Tells us nothing about all the numbers between 1 and 100, so range isn't great, but there we go. Range is highest minus lowest, but it's what we want is something a little bit more substantial, like standard deviation, which looks at every single number and gives us an idea of how far it was spread. So I've come up with an example here, just to give some. Standard deviation sounds complicated, but it's not. Okay, let's just look at what I like to think of. The word standard, it's like normal, average, every day. The word deviation is, spread, distribution. Okay, so it's saying what was normal for these numbers? What was the normal distribution for these numbers? Normal distribution's a whole different thing. That was I'm not going to edit it out. No, okay. What was the average difference of all of these scores from the mean? Is basically what it's saying. There's a mean. No matter what scores you've got, there's a mean. And it's really saying, on average, how far were the scores from the mean? Were they really close to the mean? Were they spread from the mean? So let's look at this example. Say I check the prices for a certain model of laptop. JB Good Guys Laptops R Us. That sounds made up. And domain. All right, 720, 730, 750, 760. Already looking at that, I'm saying the data wasn't spread that much. It's not like there was someone was selling it for 400 and someone was selling it for 1200. I'm no expert in the field, but it's like, okay, it wasn't a huge range. Now the average of these numbers, 720, 730, 750, 760, add them all up, divide by 4. The average is 740. Can I have a pen, please? Thank you. The average is 740. And all prices are $10 to $20 from the mean. Look, that was, if the mean is 740, that was 20 under the mean. That was 10 under the mean. That was 10 over the mean. That was 20 over the mean. So it was really normal to be $10 to $20 away from the mean. And the standard deviation is approximately 15. That's just a very rough interpretation, but still, that's what it is. Standard deviation is approximately $15. So if someone was to say just some random data, I checked on prices of I don't know what, and said the standard deviation was $15, well, that doesn't tell me much. Was the standard deviation $15 on an item that costs $100? Well, that's a bit. So some were selling it for, it was normal to be seeing it for $85. It was normal to be seeing it for $115 if the standard deviation was 15. So that's a bit of a range. What if it was a $20 item? Well, a standard deviation of 15 is horrendous. Horrendously bad, horrendously distributed. That's saying some were only charging $5, but plenty were charging $35. That's a horrendous standard deviation. That's a big spread of numbers. But if the standard deviation was $15 for someone trying to buy a $22,000 car, SD $15, that's a tiny standard deviation. So you're saying that it was normal for dealers to only be selling it for $22,015 or 15 under it? So standard deviation alone doesn't tell you anything until you know standard deviation and the mean. Together they give you some idea of how the data was distributed. So we need to calculate it ourselves. And delete that. Here's the formula, which I know looks hard, but really it's a happy formula because one, it's provided to you on the formula sheet, and two, it just tells you how to do this whole next bit, manual calculation of standard deviation. It's going to be our guide to remind us what to do. And it may not look like it, but it is. Okay, let's go to things already started happening here. Let's go to this table. So here we're doing the table for the laptop prices. So the scores I got 720, 30, 50, 60. Okay. Then we make a column which is the difference between the score and the mean, which is what I did before. I said that was 20 under the mean, 10 under the mean, it was a plus 10, plus 20. So the heading on this column, I put a D there just to say, look, it's the difference, but it's x minus x bar, okay? Get the score, 720. We know the x bar is 740, so it's 720 minus 740, 730 minus 740. So hopefully that first column makes sense. It's just the difference between the score and the mean, with some plus or minuses, okay? If we now go down to the next page, look at if I try to just average them up. I'm trying to average up a minus 20, a minus 10, a 10 and a 20. If I want to average them, I would add them all up. And they all add up to naught, and then naught divided by 4 is naught. It tells me the average of these scores, or the mean of these scores, is naught. Well, that's true, like I say, but we hit trouble. The average difference that I want to think of in standard deviation is, I don't actually care whether you're above the score or below the score. I just want you to count as a difference. So it's not true that the standard deviation of this data was naught. A standard deviation of data of naught would mean every shop I went to was charging the same amount. There was no spread, there was no range, there was no distribution. Okay, so clearly the answer isn't standard deviation of naught. What we want is to make all of the numbers positive. I want to see these negatives as positives because I just want a difference between the prices. I don't care whether it's up and I don't care whether it's down. So what was decided back in olden days was, what gets rid of negatives? Squaring does. So this was the column from the previous page where we looked at the differences. Now we've got a different squared column, which is x minus x bar, the same name as the previous column. It's just getting squared. And again, why square it? Because a negative times a negative becomes a positive. And notice they all become positive. Now these, I can find a good mean of these. Okay, that's not going to give me a mean of naught. So let's do it. Let's find that mean, and here it is here. Add them all up. Here we go. So the average d squared is equal to 250. So is that our standard deviation? Not quite, because the definition of standard deviation is, what's the average square of the differences between the prices and the mean? It's just the difference. I don't want that squared there. So how do I undo a squared? Square root. So if the average d squared is that, then we can say approximately the average d is going to be the square root of that. And as you see down here, the square root of 250 is about 15.8. So on the previous page I said, look, the standard deviation was about 15. Wasn't lying. 15.8 is about 15. Okay, so this is how we calculate it. Every single standard deviation, when we use the standard deviation button on the calculator, or the mode on the calculator, yeah, that's what it does. It gets every score, takes away from the mean, squares it, finds the average of all the squared ones, and then square roots it, and that average distance is our standard deviation. So in summary, what did we do? Well, here's what we did, this table. We had an x column of the scores, we did an x minus x bar column, and we squared that column. I then got that here, the sum of all of the squared scores, and said, well, the sum of all of them was 1,000. I divided it by 4 because there were only 4 scores to say that that was 250, and then I square rooted it. That's the formula. What did we just do? We said, let's look at it on the previous page. There was that horrible formula, and I was trying to convince you, oh, it's actually pretty nice. It says, now this little symbol is standard deviation. That's a little sigma. We talked about sigma. That's sigma lowercase. In previous weeks we've looked at this sigma, which, yeah, that's just sigma uppercase. When we saw that big sigma, we called that sum. That just meant sum. this little sigma means standard deviation. And the formula says, well, sum up all of your differences. All my differences are x minus x bar. And then we got them and squared them. And then we summed them up. And then we divided by the number of scores to find the average isn't squared. And then we square rooted them. That formula is telling us exactly what we just did in that table. I might be going overboard a bit by saying, wasn't this? It's fun. But bear with me. Let's look at exactly what we did again with this next example. There's us doing it. Here's an example. Okay, good. Because that's exactly what we did. All right, that's just repeating that. So here's a further example. We've got Kay, all of her scores that she got in 6 spelling tests. 6, 1, 2, 3, 4, 5, 6, good. Louise got those 6 scores and Mike got those 6 scores. They all got the same mean. Now, let's just look at them. Kay got 19, 29, whoa, she got a variation. Louise, 16, 17, 16, ooh, that's really tight scores. Mike, 20, 12, 19, 13. I reckon that's even more spread than Kay. Just from looking at it, I reckon my standard deviations, I'm going to take a risk here, and this could backfire in my face. I reckon Louise's standard deviation, she's normally only 0 or 1 away. Her standard deviation is going to be barely a half, something like that. Kay, well, when she was 16, she was 3 above, she was 4 above, she was 7 under, she was 1 above, she was right on track, she was 1 under. I reckon they're going to add up to about standard deviation of maybe 2 or 3 was normal. 2-ish. And maybe Mike, hey look, don't spend too long on this, 3-ish. So that's just me just putting it out there. Now let's do it properly. Here's Kay. First of all, I want to check. What did I say? 2-ish, 3-ish. Oh, I wasn't too good. My 2-ish was really 3.6. My 0.5 was 0.6, good boy. My 3-ish was 3.7. Okay, I'm not the world's best standard deviation estimator, but hopefully you still got the concept. You can still look at data and get some rough idea. So K's scores were here. We know that all of the means were 16, so this column may as well just be called get your score and take off 16, which gave us all that. And then we knew that we had to square everything because we didn't want negatives. And then we said, well, the average of this d squared column is get your 76 and divide by 6. So the average d squared was the answer to that, and we had to square root it. So again, we are using this formula. Remember, this sum of x minus x bar squared is just that number. N is just the sum of how many scores we've got, which in this case there's 6 scores. So the 76 went over a 6, got square rooted. We did the same for all of them, and again, yes, okay, so Kay and Mike was the furthest spread, the biggest standard deviation, but not by much off Kay, and Louise was really, really consistent. Consistent means, yep, low standard deviation, fantastic, and there's our summary. So hopefully that in particular shows that the use of standard deviation, the measure of central tendency of means said they all had identical scores. Well, they did have identical means, but standard deviation gave us a whole different perspective on how they did. Consistency versus inconsistency, widespread of data. The next bit goes on to standard deviation in the calculator, and we've already got a video for that. Okay, Scott's already put a video up there, exactly pressing the right keys for the FX82AU plus, which is the same as the plus 2. I think they're all the same. I've got instructions in on Blackboard, so let me know if you have any issues with it. But there's the written instructions, and on the next page, how to add a frequency column for when we don't just have individual scores. I've got 1, 8 times 2, 12 times 3, 10 times. Our calculators can still do all that, but check out the other sister video we have, and I hope that was useful. Week 10, done. See ya.